Hello everyone and welcome to this first lecture in this course. Thank you so much for registering for this course and I hope you really make the most of it. In this first lecture, I'm going to talk about what this course is all about. Just a brief overview of what you can expect in this course and why I created this course. So to begin with, this course deals almost exclusively with understanding the switching of power electronic converters. That's all we are doing. We are just looking at switching strategies of power electronic converters. This book will not deal with any specific applications or examples. So for example, we will not deal with electric vehicles, or we will not deal with UPS or active filters or anything else any other specific application that one may expect in a power electronic course, right? There may be references once in a while. For example, when would such a particular converter be used? It could be used in an electric vehicle, it could be used in integrating a photovoltaic panel to the grid, but there will be no specific application being discussed in any of the examples. The entire focus is only on switching strategies. That is it. So then the question here is, what are we trying to do with this course? What we are trying to do with this course is to answer this question. What can we achieve with a power electronic converter? This is the fundamental question that we are answering throughout the course. We have several power electronic converters that are used very often in industry. And most of these, for example, of course, one can think of any power electronic converter constructed in any manner, and there are several special constructions in special applications. But in a vast number of industrial applications, you will find a certain steady topology, certain commonly found topologies used over and over again. And there are reasons for this, for several reasons, such as, for example, the ready use of packages available. For example, you can now find intelligent power modules or even combined packages where the topologies are already present. And these will also be discussed in this lecture, in this course. So this is what we are trying to do, that with these commonly found topologies, what can we achieve with them? And this is a question which is not quite often answered in other courses. Right? Other courses will present examples and be done with it, but I would rather stretch it a little and figure out how we can analyze a particular topology and extract the maximum out of a power electronic converter. So this course will start with switching strategies from the most basic. So we are going to start with a single device. We are going to start with converters with a single device, and even before that, we'll talk about pulse width modulation in the most basic terms, with a background from signal processing to describe how pulse width modulation actually has an improvement and how modulation can be looked at in other concepts. Like for example, how is modulation used in signal processing or in communication? So this is what this course will start with, and as we progress, we will go into more and more complex converters. We'll talk about the half bridge module, we'll talk about the full bridge module, we'll talk about the three-phase module, and in all these cases, we talk about different ways in which we can think of switching strategies for these different modules, right? Because all these modules are used in a variety of applications, and in all these applications, you would need to vary your switching strategy in order to extract the maximum out of your converter. So this course is heavily based on simulations. Almost every strategy that will be described with a simulation, right? So in this case, I would be going through the simulation bit by bit. So this is not really a case where I would say this is the simulation and go ahead and build it and now we'll analyze it. I will actually build the simulation bit by bit over several lectures. So a simulation may actually last for 1 hour or maybe even 2 hours. The very last section on three-phase converters, the space vector pulse width modulation simulation will last for almost 3 hours, because that's the amount of detail I would like to go into. I would like students to be able to go into each and every detail and be able to code along with me so that they know every basics of simulation or every detail of simulation. So if simulations is your cup of tea and you would like to learn something with simulations, this course is definitely for you. So now, one of the reasons why I actually focused only on switching strategies and rather on applications is that most other books which deal with applications do cover some of the switching strategies. So for example, in any book, if you were to look at a book on renewable energy and renewable energy integration, these books will deal with the control of converters used in these applications, like the integration of a solar photovoltaic panel to the grid or the integration of a wind turbine to the grid, right? So they will discuss the control and also the pulse width modulation strategies, but they will not go into the details, because remember, these books are more about the application rather than the details of the switching. And in some of these cases, some of the advanced switching strategies are not very easy to understand. They are quite difficult to comprehend. And that is the reason why I have this course in which I'm going to talk only about switching strategies, nothing else. I'm not talking about closed loop control. I'm not talking about the actual application. I'm not talking about any other system application, like how would the power electronic converter behave with other power electronic converters. None of these discussions are there. We are only talking about how to provide gating signals to a power electronic converter. That is it. Completely focused only on that. So the reason is, and that's one of the reasons why I also created this course, is for many young engineers who are starting a project. So if you are, let's say, an undergraduate who's about to start his final year project, or for that matter, you are a graduate student doing your master's and you're about to start your project, it becomes quite a challenge to be able to actually start the project when the advanced strategy is not very easy to understand, right? When you do not have a deep understanding of pulse width modulation strategies applicable to different kind of converters, it becomes difficult to go ahead and jump into an actual research project, because the research project assumes that you know all these, right? And that is the reason, to fill this gap, I was hoping that this course would be of use to such kind of people. And I'll talk about this very soon when I talk about who are the target students in this course. So this course uses a slightly different strategy towards describing power electronic converter switching strategies, right? In most other books, pulse width modulation is presented. This is the strategy. This is the result. This may be the frequency spectrum, and that's it. In this course, I look at it in a slightly different way. I look at these as puzzles, right? So for example, you have a topology of a converter. Now the question is, what can you do with this converter? What can you not do with this converter? What are the allowable switching states? And gradually, how do you extract the most out of your converter? That is, if particular switching states results in particular output voltages, and those output voltages are useful, then how will you use them to the maximum? And with this, we then gradually solve these puzzles to develop a switching strategy, right? And this is the idea behind this, is to give these tools to young engineers so that if they do reach out to a more complex topology, they know how to analyze these converters as well. So this is the idea, is that we use this reasoning and logic rather than just mathematics, right? This course will not have much of mathematics. It is a lot of reasoning and logic, right? What can be done? What cannot be done? Why should it be done? What can result if you do something like this? So the idea is, as I said, is to understand how you can assess the capability of a converter. That is, you have a converter, it costs so much because there are so many devices, but so many devices can also result in flexibility. It results in more capability. And therefore, to get the most out of your converter, you must be able to use your converter's capability to the most. And that's what this course is all about. So in this course, I'm going to use only free and open source software. Alright. Again, you need not do that. You can come with your own circuit simulator if you have. If you are already comfortable using your own circuit simulator, which could be either proprietary or it could be another free and open source software, by all means do so. But I am a great proponent of free and open source software, and that is why I use Python programming in this course. And I also use the open source circuit simulator Python Power Electronics. And a part of the reason for that is that I am the creator of Python Power Electronics, which I will talk about very soon. Now, all switching strategies in this course will be realized using Python code, and I will try to use raw Python code, which means the most basic Python code, without using too many advanced packages. And the reason for that is that if it is realized in such a way, using basic Python rather than NumPy or some of the other scientific packages, it is easier to translate them into code for a microcontroller. So if you are looking for a hardware implementation and you're trying to figure out how a switching strategy can be translated into a hardware implementation using either a DSP based microcontroller or an FPGA based microcontroller, if the switching strategy is in basic code, right? Basic code, it is much easier to translate it using either C for a DSP based microcontroller or using maybe VHDL or Verilog for an FPGA based system. So again, as I said, there will be a lot of theory where I will be discussing how converters behave, but these theory lectures will be using the minimal amount of mathematics. I do not want these courses to become mathematically intense because I want these courses to be useful for those who are working engineers and who do not have much time to be going into the depths of mathematics. I will be using visual representation in a great deal. So almost everywhere I'll be drawing a lot of circuits, a lot of circuit diagrams. I'll be talking about how circuit diagrams can behave in different ways. I'll be talking about conduction paths. What if one device conducts? What if another device conducts? How will the current flow? These are the things I'll be talking about in this course. Now this course will also bring in a few useful techniques which you can always use later, and these are such as how to perform frequency analysis on a particular waveform using FFT, which is fast Fourier transform, and also things such as how to plot a vector diagram using Python. And all these will use not just Python, but in some cases will also use NumPy and Matplotlib. Right? NumPy is basically an advanced library for dealing with matrices and other advanced concepts, and also Matplotlib is used mainly for plotting. It's equivalent almost to MATLAB, and it has a lot of advanced functionalities when it comes to plotting. So during this course, this course is mainly a simulation based course. So I will be mainly describing switching strategies through simulations, right? However, there will be times when I will also talk about how there may be challenges in implementing certain switching strategies in hardware. Because remember, hardware implementation can vary drastically depending on the actual microcontrollers which are available. If you have an advanced microcontroller like a 64-bit microcontroller or a very large FPGA, then in that case, you do have a lot of flexibility in actually implementing your code. However, some of the more rudimentary microcontrollers may not allow you to do much, right? So there will be challenges in such cases in implementing some of these switching strategies in some of the more rudimentary microcontrollers. And for that reason, I will be discussing to a certain extent, not to a great deal, but to a certain extent, what can be done if you do face such challenges in implementing switching strategies in hardware. So with this, I would like to welcome you to this course. And in the next few lectures, I will talk about some of the other details of this course, such as who would benefit from this course, what you need to do this course, and how you should best complete this course. So again, if you have any doubts about what I talked about, of course, you're most welcome to use the Q&A forum and post your question there. If not, I will see you in the next lecture. Thank you so much for listening and see you soon. Goodbye for now.